Okay, welcome to our last set of notes, slides 21 to 26 in the last chapter of Organic 2. Oh my goodness. All right, so now we're switching gears. We've spent the last few slides discussing how to generate amines, right? How to put one group on selectively, or even 2 or 3 groups if we use reductive amination. Now we're going to switch gears and talk about the second way we can use amines, which is as leaving groups. Now, we can't do all of the things we did with an amine like we did with an alcohol in the sense that, let's just, protonate it, form a better leaving group, which in this case would be water, and have it do either, SN2-like chemistry or SN1 chemistry and go on from there, right? Where you would lose water as the leaving group. The leaving group would be water. Now, here's why it's different. An alcohol is neutral. Water is neutral. Under acidic conditions, you're tossing out a water molecule, which is neutral. It's perfectly okay under acidic conditions to toss out a neutral molecule. So why is this protonation important? Well, if we were under acidic conditions or we're in solvolysis protic type conditions, it's very difficult to remove a leaving group that's basic. This is sort of the premise. If you go all the way back to the beginning, a leaving group is good when not a good base, right? Think about chlorine minus, bromine minus, iodine minus. Chlorine minus, bromine minus, these are great leaving groups. Why? Because when they leave as a negative charge species, they are perfectly stable with their negative charge. They are also not very basic. I mean, thank God, right? Sodium chloride, salt. You don't put it in your mouth and go, it's a base. Chlorine minus is a terrible base. So is bromine minus or iodine minus. They're terrible bases because as a negative charge species, they're pretty stable. REO tells us so. Now, OH minus is a pretty decent base. It's not great, but it is a pretty good base. It's a way better base than chlorine, bromine, or iodine minus. So if OH minus is a good base, then it's not a good leaving group. That's why it was important to protonate the OH. We wanted to protonate it so that when it left, it wasn't a good base. What's the problem under basic conditions if we consider NH2 as our leaving group? All right, so if I have a base like NaOMe and I wanted to do an elimination, good God, what would I be doing? I'd be forming my alkene, but the conjugate would be, or the leaving group would be NH2 minus as the leaving group. Oh my God, this is a very strong base. Think about LDA, right? LDA was a strong, bulky base we used to make enolates. Nitrogen minus is a very strong base. Why? REO tells us that the atom is not very electronegative. They're pretty generous. They're generous and they're overly charged negative. Man, they are looking to react with something. So this is not going to fly. Nitrogen minus is a terrible leaving group. Okay, well, let's do what we did with alcohols. Let's protonate it. Let's make it NH3 plus, and then consider, some conjugate base reacting with it. Here's the other problem. Equilibrium-wise, it's not going to like this either, because the conjugate is NH3, ammonia. And ammonia is a pretty decent base, right? Amines are pretty good bases. So again, the nitrogen's not a great leaving group. We don't want it to be a good base when it leaves. And so it's also improbable. I drew the arrows like this. It's not just that it's a good base in this case. What do you think the bigger problem is? The bigger issue is that we're operating under highly acidic conditions. So making or generating a base as a leaving group to shove out is very difficult to do when you're under highly acidic conditions. So we've got to sort of trick the chemistry into making nitrogen a better leaving group. Here is the fix. And we're going to bring back the problem of overalkylation to actually help us make a much better solution here. Okay, so let me bring one more thing in. NH3 plus is a great acid. The other problem is that the elimination is not going to happen because the most acidic proton you can actually grab now is probably going to be the hydrogen on the nitrogen. That is a highly competing acid-base reaction. Okay, so how do we fix that? Well, what we're going to do is we're going to overalkylate our nitrogen so it doesn't have any proton sources on it anymore and make it a much more stable leaving group. Okay, here's what we're going to do. We're going to take our NH2, we're going to introduce something cheap like methyl iodide, and we're going to do our SN2 reaction. And we've alkylated it. And then we add K2CO3, our potassium carbonate, which just does some acid-base chemistry to remove the extra proton. And we're just going to keep doing this until we've completely overalkylated. So an excess of methyl iodide just has us do another SN2 reaction. Now I have two alkyl groups. There's still some potassium carbonate around. Takes off the extra proton in an acid-base reaction. And I'm going to do this one more time. I have now completely overalkylated the nitrogen. This is exactly what I was trying to avoid when I was trying to simply place one group onto my nitrogen. Now I'm going to have it use itself to my advantage, okay? So now I've overalkylated the nitrogen, and it is now not susceptible to be deprotonated anymore, and so I don't have to worry about that acid-base competition. I can now use, in the second step, once it's overalkylated, I throw in some silver oxide, which is actually just a wet source of OH minus. I've written that right here. So this part right here, it's just kind of like a wet OH minus source. And this is where I do move this. And I do my elimination. It's going to do an E2. And I end with the product shown. The nitrogen leaves as trimethylamine, And I've also generated some water after the OH minus grabs the proton. But from a carbon perspective, I've done an elimination whereby the nitrogen was the leaving group. Now, these conditions are actually run kinetically, so they tend to run at a low temperature. And when you're eliminating, you tend to, well, you're always going to be following an E2 reaction. And under low temperature conditions and the conditions of the silver oxide, you actually favor the less substituted alkene. This is called the Hofmann elimination, and you favor the Hofmann product, which is the kinetic product. When you have a choice of which side to deprotonate, don't go for the one that gives you the thermodynamic, more stable double bond. These conditions all around end up working like kinetic conditions, and you're going after the more easily to grab, more exposed proton, and this one leads to the kinetic product, right? So you're actually making the easiest alkene with the most exposed hydrogen. Understand that when you run these types of reactions, they are following E2. So you got to go back to your elimination reactions and understand that mechanistically you need to have anticoplanar geometry in order to eliminate. So you got to go back and revisit your anticoplanar configurations. This is showing you what that means if you were to eliminate across 2 and 3. The issue here is that this is the kinetic product. And this is going to be the major product in a Hofmann elimination, because the double bond formed is grabbing the hydrogen that's on carbon 1, which is primary and way more easier to access than, say, the anti-coplanar one at carbon 3, which is secondary. In these reactions, you do the kinetic thing. Go after the easier to grab proton. This next slide, 24, allows you to have some practice in this array. So I'm going to leave this one to you guys to do, and I'll post the answers on my courses. And this brings us to one of our last slides, amines as nucleophiles. So this is all review. This is just in context of old reactions that we've seen, so I didn't put them in flashcard mode because you guys already have these. But if you go back to our aromatic chapter, I told you that there was a reaction that was not actually in the aromatic chapter because it actually was in the amine chapter. So here it is. The aromatic chapter notes I gave had this nitrosation where R was actually a benzene ring. But R doesn't have to be a benzene ring. R could be a tertiary carbon. You do HONO, H-N-O, HONO, or the sodium nitrate version of it, in excess acid and water, you end up forming this N2 species, which, under these conditions with heat, will leaving behind, hopefully, a tertiary carbocation. N2 gas leaves, and so these carbocations are best when they're formed on tertiary or secondary carbons. But R does not have to be a benzene ring. I just like showing that in the benzene chapter because I feel like it opens up the door to a few more reactions that you can run, but you can do it on a regular amine system. And then obviously you have a carbocation, so you can finish off an SN1, however you want. You can also make amides with them. So here's where we were using them, right? We were using them to make an amide. We had an acid chloride or an ester, and under the right conditions, we were doing an in, up, down, out, and we were forming the amide. So we were using amines to form amides. Going back to the ketone aldehyde chapter, we were using amines, primary amines, to react with ketones and aldehydes to give us imines, and we were reacting secondary amines with ketones and aldehydes to make enamines. So we've been using amines as reagents or nucleophiles all along, right? That nothing is new here. This is just a reminder that you guys are comfortable in a way that you didn't maybe recognize that you were comfortable working with amines as nucleophiles. Alas, that is it. That is the end of Organic 2. You may rejoice. You can actually dance around while watching this video and not be having to show your excitement in class in front of me and make me sad, but you have made it through Organic Chemistry 2. But I just want to warn you that if you find yourself experiencing sleeplessness, unexplained emptiness and feelings of loss, anxiety about knowing that there's no more organic chemistry to learn, or you just feel this need to push electrons in other classes even when they're not requiring you to, or just, sheer boredom these days, you may be suffering from organic chemistry withdrawal. But I just want you to know that there's a cure. You may contact me and let me know that you're interested in serving as a workshop leader for the fall for the incoming class of Orgo 1. Perhaps you would like to be a workshop leader for Orgo 2 and keep it fresh in your brain. Perhaps you're aiming to do an MCAT soon and you just want to stay limber, right? Or maybe you're interested now in minoring in chemistry and you'd love to be able to do it in a way that where you only did organic chemistry type courses. And maybe you just are so happy you're like, see ya, I'm done, right? Either way, we do have a lot of advanced organic chemistry courses beyond the two that I'm mentioning here. I think Dr. Cody is offering what is it? It's an advanced process chemistry course in the fall. There are Spec ID courses. We have advanced physical organic if you like orbital theory. Lots of stuff that you can do focusing strictly on the organic and really not needing all the calculus. Also, if your major does not require any other chemistry courses, you could count Biochem 1, Biochem 2, inorganic chemistry. You can see what all the hubbub is over the rest of the periodic table, all those metals to the left. So there's lots of classes that you can take to really consider a minor in chemistry. Beyond Orgo 2, you can take 3 more 3-credit classes. You could take 2 3-credit classes and then serve as a workshop leader 3 times. There's lots of different ways of going about becoming a chem minor. So if you're interested, please throw an email out to me or give me a ring and let me know that you're interested. I am the minors approval person. I guess I'm like the one you would talk to be a minor in chemistry. I don't know what that title is, but you can make one of those up for me too. Hope you guys are happy with having to be able to watch these lectures over again, and I would love for your feedback on any and all of this content in the online form. So happy studying, and I'll see you during our Q&A sessions.